of a galvanic cell. So to understand the standard electron potential of cell, first understand the standard electrode potential of half cell, because that is more important, and with that only you will get the standard electrode potential of the whole cell. So to understand the standard electrode potential of the whole cell, just see this half cell. Just see this half cell. Let's suppose I am seeing this half cell now. So if you see this half cell, focus only on this half cell, right? So if you see, there is an electrode here and there is an electrolyte here. This is the electrolyte and this is my electrode. In fact, you see here also we have electrode and electrolyte. We are focusing only on this part, right? So at each of this interface, I'm talking about, right? So there is a tendency of metal ions from solution to deposit on the metal. So there is a tendency of copper plus in the solution, right, to get two electrons somewhere, to get electrons from this wire coming back, right, merge these, form copper and get deposited here, right? So copper plus is nothing but copper sulfide. So copper ions from the copper sulfide is a tendency to form copper. In this case here, reverse scenario, there is a tendency of zinc from this metal to become Zn2 plus and give electrons, correct? So there is a tendency here to become zinc ion from zinc, and here there is a tendency to become copper from copper ion. Correct? So this tendency from copper plus to become copper, this gave it a positive charge, and this tendency from zinc to zinc plus gave it a negative charge, because zinc to zinc plus, it will liberate electrons and thus it will get a negative charge, right? So if you see for a given half cell now, let's suppose the equilibrium, and there is a separation of charge between electrode and electrolyte, right? So the potential difference between electrolyte and electrode is called electrode potential. Please note, we are not talking about the potential difference between these two electrodes. We are talking about the potential difference between the electrode, this guy, and the electrolyte. Let me write here. Potential difference between electrode and electrolyte for a given half cell. We are focusing only on one half cell, right? Is called electrode potential for that half cell, right? And since electrolytes is also involved, so it depends on the concentration of electrolytes also matters. Concentration matters. So currently we'll take only 1 molar liquid. We are talking about all the 1m. If it is a liquid, we'll take about 1 mole of liquid electrolyte. If it is a gas electrolyte, we'll take about 1 bar gas pressure of electrolyte. So we'll talk about all standard pressure now, right? So if you talk, this is the electrode potential at any concentration. But if you take everything at STP, right, 1 mole. So at STP and 1 mole, this electrode potential which I just got will become what? Standard electrode potential. Standard electrode potential. Correct? So we have something called electrode potential, that is nothing but the potential difference between electrodes and the electrolyte for a given half cell. That is nothing but electrode potential for that half cell. Similarly, if you if this concentration can be 2 moles, 3 moles, can be any moles, right? The temperature can be anything, the pressure can be anything. But if you standardize those values, you just take 1m you take to 98 Kelvin temperature. So at that specific values, right, at STP, whatever electrode potential you will get is that becomes the standard electrode potential for that particular half cell. Correct? Now again there is a confusion actually. See, here we are having reduction, here we are having oxidation. Correct? So again, in if you say standard electrode potential or electrode potential, are you referring to reduction or are you referring to oxidation? We have to choose one, else it will be a confusion, it will be a chaos actually when you solve problems, because one will have negative sign, one will have positive sign, it will all confusion. So what happened is, to avoid all the confusion, the IUPAC came with a convention. It told that standard reduction potential will be called electrode potential, or will be called standard electrode potential. Right? So it is reduction now which will be called as electrode potential. So for example, for this I got some value, I'll just keep it like that only. But for this I got some value, so whatever value I got some volt, right? For example, this I got X volt, that is correct because that is my reduction potential. Here, if I got oxidation potential as Y volt, then my electrode potential will be minus Y volt. Because, flip it, because now we are saying that it's always, note here, standard reduction potential is the one which has become electrode potential now. That is official. And to remember this, rich people rule, right? Because if you see, this rule is made by rich people at IUPAC. So rich is what? Reduction, P is potential. So reduction potential has become electrode potential, correct? So the rich people has selected reduction potential as the standard potential. So remember, if you want, you can take it or you can ignore it also. So that is the point I'm trying to convey here. So when you talk about the reduction potential, that has become an electrode potential now as per IUPAC now. And that's again why IUPAC has chosen, we don't know. They just chose it and we have to stick to it. That is my standard reduction potential or reduction potential, right? So if you see, this is my anode and this is my cathode. Anode means oxidation, here we are having oxidation, cathode is reduction. So anode is half cell in which oxidation takes place. So since now I have taken electrode potential as a reduction potential, so this will have negative potential. Correct? It will have negative electrode potential. Why? See, because this will always have positive oxidation potential, right? Because here oxidation is happening. So it will have positive oxidation potential, that means it will have negative reduction potential. Now it has been accepted widely that reduction potential is my electrode potential. So it will have negative electrode potential, correct? Positive oxidation potential implies negative reduction potential implies negative electrode potential. So it will have negative electrode potential. Here in this case, positive reduction potential because reduction is happening here. So that implies it will have positive electrode potential. So hope you understand what I'm trying to say. Now since there is a confusion here, there is a new term called electrode potential here introduced, and that is always the reduction potential. So in reduction half, reduction is happening, so reduction potential is positive. Since reduction potential is positive, my electrode potential will always be positive. In the oxidation half, since the oxidation is happening, oxidation potential will be positive. That means reduction potential will be negative. Reduction potential is negative, that means electrode potential will also be negative. Right? Now if you see, there is a potential difference between these two electrodes. Right? The moment you turn on the switch, the current will flow. right? The current will flow from, the electron will flow from anode to cathode, and the current will flow in the reverse direction, right? So this potential is called electrode potential of cell. So electrode potential of cell is nothing but E of cathode minus E of N. Please note why? Because see, cathode we have reduction, right? So generally this is in positive. This is positive. So it will have a positive value minus, and this will have a negative value. Overall you will get positive value. Hope you understand why we are taking cathode minus anode, because if you take anode minus cathode, it will come negative minus some positive value, it will come out of a negative value. So it will be, you have to say that my electrode potential is minus 7.1 volt for a battery. It doesn't look good. So again, this is also by IUPAC. This is what IUPAC has given this, that electrode potential of a cell is E cathode minus E anode. Correct? So that is what we have learned in this slide, that my electrode potential is nothing but reduction potential as per IUPAC for a given half cell. So the electrode potential of a cell is nothing but electrode potential of a cathode minus electrode potential of anode. And please note, when you talk about electrode potential, I am talking about the reduction potential. Don't take oxidation potential here, right? Because I am talking about electrode potential, that is nothing but reduction potential. So we will always take reduction potential only, just to avoid any confusion. So as I told that the potential difference between two electrodes in a galvanic cell is called cell potential, right? And that is nothing but electrode potential of my cathode minus electrode potential of anode. This has positive value, this has negative value. So overall it comes out to be positive value. Correct? And it is measured in volts. And I told why it is measured in volt, because it is in the honor of Alexandro Voltas. Right? So the cell potential is the difference between the electrode potential of, or nothing but, this is nothing but the reduction potential, as I already mentioned, of cathode and anode. Please note it is cathode minus anode, not anode minus cathode. Correct? So it is, this value is called electromotive force when there is a condition here. So now this value will be called EMF, or electromotive force of the cell when no current is drawn from the cell. Please note, this value is called electromotive EMF when there is no current. For example, in this case, now there is a current drawn, right? So this is not EMF. If you apply some voltmeter here, you won't get EMF. But in this case, since there is no current that is being used, so whatever V you get becomes the EMF of the cell. Right? When I say EMF of the cell, that means the cell potential of the cell when there is no current drawn from the cell. Right? Now there was a confusion. Right? Some people used to keep anode on the left, cathode on the right. Some people used to do the other way around. Some people used to keep cathode on the left, anode on the right. And there was a confusion. So again, IUPAC name came with the convention that anode will be on the left and cathode will be on the right. A good memory tip is AC, air condition. A come first, C come first, C come next, right? Air condition runs on what? Electricity. I mean, the other time is you get a CA. There is no link of CA and the current, so you can ignore that. AC, you know that AC runs on electricity. So there is a link here. Anode on the left, cathode on the right. Right? This is a representation actually. Anode always has to be on the left and cathode always has to be on the right as per IUPAC. Now the galvanic cell is represented by putting vertical lines between the metals and the electrolyte. So for example, I have metal. I'll put a vertical line and I'll put electrolyte. This will be for the anode. And then there will be another electrolyte for the cathode. I'll put a double vertical line. I'll put an electrolyte here. And then there will be another metal in the right side. For example, it will be metal zinc. Here I have zinc sulfate. Here I have electrolyte copper sulfate. And here I have metal copper. So if you see, B is my, sorry, this is C, yeah. Right? Anode, I have zinc and zinc sulfate. Zinc. And this is my zinc sulfate. And cathode, I have copper and copper sulfate blue solution. So this will I'll represent as zinc solid, and this will become Zn2 plus, that is an aqueous mode, and there is a double slash Cu2 plus aqueous mode, and then I have copper solid. So that is the representation of a galvanic cell. Anode come first and then cathode. Correct? So this is a representation for this Daniel cell actually. Daniel cell is also nothing but a type of galvanic cell. So using this convention, let's suppose I have to find the EMF of the cell. Right? So EMF of the cell is always positive. So EMF of the cell will be what? E of cathode minus E anode. You can also say E right minus E left. Right minus left. Right? Right comes first. Right is always first, right? Right minus left. Right and then liar. L for liar. Right minus left. What is the value of E right? Copper to copper plus E reduction is 0.34 volt minus for this if you see zinc to zinc plus, the oxidation E of oxidation of zinc to Zn2 plus is plus 0.76 volt, but we are looking for E of reduction from Zn plus to Zn, correct? That is nothing but minus 0.76 volt, and this is nothing but my E naught for zinc, correct? And that is nothing but minus 0.76 volt. Total is 1.1 volt, right? So E right was my, or I can write one more step here. E right was my E of copper 2 plus to copper minus E left was E Zn plus 2 to Zn. Please note here, I am not saying E of zinc to Zn plus 2, because I am talking about the E reduction. Here also reduction from Cu2 plus to copper. Here also reduction from zinc plus 2 to zinc, because reduction is taken as official electrode potential, rich people rule, right? So with this I got 1.1 volt. That is my EMF of this cell. Now the question is, how did I find that reduction potential of copper from Cu2 plus to Cu is 0.34 volt and reduction